Hello. So today we're going to talk about topics 2.2 and 2.3 together. Topic 2.2 is just defining the derivative and using proper notation. And then topic 2.3, we're going to estimate the derivative of a function at a point using tables, graphs, so on and so forth. Okay, so first, if you recall from topic 2.1, we used this definition, this limit expression, if you will, to find the derivative of an expression at a point, or the instantaneous rate of change at a point. So the derivative function is going to be the expression that was written prior to substituting in our x value, and we denote that with this little apostrophe here. And the way that I say that apostrophe is f prime of x. So I use the word prime. I also can say the first derivative of x. If you see more than one apostrophe, then that would indicate how many derivatives you've taken. But ultimately, there's one apostrophe there. It is the first derivative. Now, using correct notation, if you look right below it, if your function is defined as y equals, you will see either y prime or a dy dx, and just kind of an explanation of this dy over dx is, if you recall, it's the change in y. Okay, when we find the slope of a line, excuse me here, when we find the slope of a line, we always find the change in y over the change in x. Those d's, dy, and dx just stand for delta y, delta x, change in. So you might see that notation as well. Now, if your problem uses function notation, f of x, g of x, g of x, h of x, right? Then you're going to see that apostrophe with the same function notation. If your problem is not indicated f of x, do not use f primes in your problem. We need to make sure that we're using the appropriate notation throughout our work. Okay, so just kind of a recall from 2.1. Can we find the derivative of each of these functions? So if you remember, I have the limit, okay, as h approaches 0 of f of x plus h minus f of x all over h. I'm going to substitute in the x plus h into my function. So I have, as h approaches 0 of, I'm going to say a 5 x plus h minus 13 minus the original function, which was just a 5x minus 13 all over h. If I do a little distribution, I have, as h goes to 0, a 5x plus 5h minus 13. I'm also going to distribute the negative. So that would be a negative 5x plus 13 all over h. And the fun part, gone. 5x's go away. The 13s will also cancel. So I now have the limit as h approaches 0 of 5h over h. And if you reduce those h's, we get the limit as h goes to 0 of just 5. And if you take the limit of any constant, you just get that constant. So I get 5 to be my answer. Now, normally it's an expression of x, but I also want to be clear on how I'm going to write this. So the derivative, I want you guys to have good notation. The derivative of this function, because it was f of x equals 5x minus 13, I can say f prime of x is just 5. Okay, so the original function was 5x minus 13. I can then say f prime of x is 5. Okay, now if you take a look at part B, all right, we're going to change colors here. We'll go to green. Again, if I start with that limit definition, I have a 3 x plus h squared minus, now there's only one term, so I'm just going to subtract the original function all over h. So now I need to square that binomial. So I have a 3 times x squared plus 2xh plus h squared minus 3x squared all over h. I'm going to distribute. So I have the limit as h goes to 0 of a 3x squared plus 6xh plus 3h squared minus 3x squared all over h. And again, the fun part, 3x squareds cancel. I'm going to give myself a little bit more room here. I'm going to say the limit as h goes to 0 of, I have a 6xh plus 3h squared all over h. If you reduce an h out, I have just a 6x plus 3h. And if you do a direct substitution with your h, we just get 6x. Now, our original function was y equals. So if I know I have y equals, okay, 3x squared, then I can say that y prime is a 6x. Or you could have also said dy over dx is a 6x. Those mean the same thing. Okay, so we're finding the function or the expression for the instantaneous rate of change. Okay, now we have one more. Again, this one has a radical. If you remember from the last video, you might remember we use the conjugate. So I'm going to say x plus h plus 2 minus x plus 2 all over h. Again, those are radicals on the top. So if I use the conjugate, h plus 2, and then that would be a plus. Remember, you have to do it to the top and bottom. I am going to distribute. We get a little difference of squares here. So I have an x plus h plus 2 minus an x plus 2. Be very careful with that negative. Over an h times the square root of x plus h plus 2 plus the square root of x plus 2. Okay, and if we combine our like terms here, I get the limit as h goes to 0 of x plus h plus 2 minus x minus 2. I'm just trying to show all my work here, guys. Again, I think you guys could probably do this in less steps. The x's cancel, the 2's cancel, and I'm going to be left with a limit as h goes to 0 of an h over an h times the square root of x plus h plus 2 plus the square root of x plus 2. Okay, the h's cancel. So I'm running out of room here, but bear with me. I'm going to write it underneath. The limit as h goes to 0 of 1 over the square root of x plus h plus 2 plus the radical of x plus 2. That's all in the denominator. Will just give me 1 over 2 times the radical of x plus 2. This is your derivative. Now, because our original function was y, again, I ran out of room, but I would make this y prime, or you can make it dy dx equals however you would like to write that notation, okay? So finding the instantaneous rate of change. Now, an instantaneous rate of change is going to be the slope of a tangent line. So just kind of some notation reminder about how to write the equation of a line. You guys might have seen point slope form, okay? Y minus y1 equals m times x minus x1, okay? So that's how we teach it in algebra, or you might have seen it before, okay? I just want to kind of show you the progression where I did the same thing from the first line to the second line, but I used, instead of y1, I put a function, the output using function notation, but otherwise the same. So at some a value, right, when x equals a, I used f of a and a, right? And then I want to see the progression to the last line, because this is what you'll see in calculus more often. Instead of m, I'm using f prime of a. I'm using the slope at a. So again, we find an instantaneous rate of change. I want you to make that connection between instantaneous rate of change and slope, right? That's what a rate of change is. So for example 2, if we write the equation of the tangent line to that function, right, at x equals 3. Now, correct me if I'm wrong. We already found the slope or the derivative for part A in example 1. So if I know f of x equals 5x minus 13, and we showed earlier f prime of x was just 5. We did that in example 1. So I need a point. So whenever I write a tangent line, you always need 2 pieces of information. You need a point and you need a slope, okay? So my point is 3 comma, now I need the y value. So I'm going to get that from the function, from the original. So 5 times 3 is 15, minus 13 is 2. And then, well, I don't know why I wrote the word slope there. The point is 3, 2. The slope is then going to be 5, because that was our derivative. And it's a line, so the slope everywhere is 5. So my point slope form is going to be y minus 2 equals 5 times x minus 3. Now, in order to receive full credit on an AP exam, we do want to make it y equals. So you can leave it as this. Oops, that should be a 2. You can leave it as that if you want. You do not have to simplify any further. We just have to get y all by itself. Or you're welcome to distribute, okay? Just, I mean, you should know how, just in case it's a multiple choice. Y minus 15 plus 2. And if you combine your like terms, I get that from my slope-intercept form. Okay, so writing the equation of the tangent line, if you notice that the tangent line on this problem is actually the same as our original function, and that's because, well, every point is going to have the same slope, so there's no real way to write a tangent line that's going to be different. But I want to take a look at part B, okay? So if we do this one, now we found earlier dy dx, right? The derivative was 6x. We did that in example 1. So you can look at your paper. We did that in example 1. So my point is at negative 5 comma. Now I need the y value, so I'm going to plug that in. So negative 5 squared is 25. 25 times 3 is 75. The slope is going to be 6 times a negative 5, which would be a negative 30. So my tangent line would be y minus 75 equals a negative 30 times x plus 5. Again, I'm just using that point slope formula. And you could, if it was a free response problem, you could leave your answer like this. Again, it's got to be y equals. Now, if you want to distribute, I get y equals a negative 30x minus 1500 plus 75, and I get a y equals a negative 30x minus 75 to be the same tangent line, just written in a different form. Okay, so those are equivalent lines. All right. Now, for the last one, we already found this derivative, so I know dy dx, or y prime, if you want to use that notation, was 1 over 2 square root of x plus 2. All right. And so my point is going to be 1 comma, if I plug 1 in, I get the square root of 3. My slope, if I plug 1 in, would be 1 over 2 square roots of 3. You do not need to rationalize. So if I write the equation of my line, I would say 1 minus the square root of 3 equals 1 over 2 root 3, x minus 1. If I add that square root of 3 over, so I can say 1 over 2 root 3, x minus 1, plus the square root of 3. And this would be my tangent line. Okay, now I would not try to distribute that. I don't think that's going to come out to be very nice. I would just leave my tangent line like that for this problem. Okay, now that was section 2.2. 2.3 is just trying to estimate the derivative or the slope at a point from a table of values, right? So if I give you this table of values, so you can see x, f prime of x, I want to estimate the value of f prime, so the instantaneous rate of change. Rate of change, right? At x equals a negative 1.5. This is what I'm trying to find. Now, if I'm going to do that, I'm just going to find the best average rate of change I can between these values, right? So between negative 1 and negative 2, I want to find that average rate of change, okay? So I'm going to use the points negative 2 comma negative 2 and negative 1 comma negative 2. And if you find the average rate of change between those points, that will then give you an approximation for that derivative. Okay, so I'm going to say here, let's try to get this going here. Negative 2 minus negative 2 all over negative 1 minus negative 2 gives me a 0 over positive 1, which is 0. So I can say that f prime of a negative 1.5, I'm going to use the approximate symbol. It's not equal to, it's approximate. If you were using equal to, that wouldn't be good, okay? It's approximately 0, okay? We have to make sure all of our symbols, all of our notation is appropriate here. It's not equal to 0, it's approximately 0. The best thing we can do from a table is make an estimate, okay? So just to do this again, I'm going to use another color. I want to estimate the instantaneous rate of change at 0.5. So I want to find the average rate of change between 0 and 1. So I have the point 0, 0. I have the point 1 comma 4. So if I did a 4 minus 0 over a 1 minus 0, I get 4 over 1, which is just 4. So f prime of 0.5 is approximately 4. Okay, that would be my answer. Okay, now state the value of f prime of negative 1 and describe its meaning in the context of the original function. So I want to know for part C, if you're looking at this here, I want to know what f prime of negative 1 is. So I'm going to go to my table of values, okay, and if I go to negative 1, okay, I'm looking at this value. So I can say f prime of a negative 1, make sure I circle the right value, is a positive 1. and describe the meaning of in the context of the original function. Well, I can say that the instantaneous rate of change at x equals -1 is 1. Okay. Now, if it's in a word problem, there would be a rate next to it, like miles per hour or meters per second or people per year. There would be a unit on that. This function did not have any context, therefore it would not get a unit. But I can say that the instantaneous rate of change at -1 is 1. So now I want to write the equation of the tangent line to f when x is 3. Well, if I do this, just like we did before, we need a point and we need a slope. Now, I have to scroll up to see my table, but we want that tangent line at -3. So let's get another color here. Let's go with blue. All right. So at -3, I know the point is -3, 0, and the slope is the very last line of the table. That would be a -3. So I could say my point is -3, 0. My slope is a -3. So I'm going to say y minus 0 equals a -3, x minus 3, minus a -3, which would really just be a plus. So I can say this is y equals a -3, x plus 3. If you wrote that on a free response, I would take it. If it was multiple choice, it would be a -3x minus 9. It would probably look something like that. Both of those answers would be correct. Okay? Write the slope of the tangent line to f at x equals 1. I just want to know the slope of the tangent line at 1. So the slope of the tangent line at 1 is just f prime of x, which is 5. Okay? So again, read through the questions. Does it want the equation of the tangent line? Does it want the slope of the tangent line? Does it want you to make an estimate between 2 points? That's what we're looking for. All right? So let's take a look at just kind of some connections between these graphs. If I give you an original function, and there should be a prime here, guys, sorry. This is the derivative. So this is y prime. If I give you original function, and this looks fairly cubic, I want you to see that this entire side, I'm going to try to color code this the best I can. This entire side is increasing. It's positive. The slope of that graph is some sort of positive value. Now it's changing as it goes, okay? But both spots that I put in blue here are positive values. Then we're going to hit the little maximum and the little minimum. And between those values, it's decreasing. Okay? So if you look here, that maximum and that minimum match up to the x-intercepts of my derivative graph. The reason being is because the slope at those points is going to be 0. Now, if you look here, to the left of the first point where it's increasing, those are all positive slopes. And you can see here that these are all positive values. Okay, now the same thing here where it's increasing on the right side of my graph is going to be also where the derivative gives me positive values. Okay. Now, it's between those where it's decreasing. And if it's decreasing, we know we have negative slopes. And because the derivative is something that finds slope, we know that that part of my graph would have to be negative. So anywhere where the original function is decreasing is going to be where my derivative is negative. Anywhere where my original function is increasing, it's going to be positive. And anywhere where we have a little maximum or a little minimum, those are typically 0 slopes on a smooth curve. Okay, so if you take a look at this problem here, all right, Now I have to zoom out a little bit so you can see all these. Okay, but I have 4 graphs on the top and I have 4 graphs on the bottom, and I want to try to match up which ones go with the derivatives here. Now, if you take a look, I'm going to try to color code these the best I can. So again, I have a 0 slope and a 0 slope. Maybe I should do that in purple because I want to color code it the same way I did the other one. 0 slopes. And this is decreasing. And this is decreasing. All right. And since those are decreasing, I know they need to be negative on my graph. And then I have a section that is increasing. All right, which would then have to be a positive. So I need to find a graph that hits the x-axis 2 times. Why 2 times? Because I have 2 little extrema here, and those are on a smooth curve, which means that they're going to be 0 slopes. So if you look, my first graph only has 1 x-intercept. That's no good. This has 2, so that's a possibility. Number 3 has 3 x-intercepts, and number 4 doesn't. So just based off of that, I know that these two would have to go together. But I want to kind of make sure you understand everything. So if you notice, to the left of that first x-intercept, it's negative because it's decreasing. To the right of this x-intercept is negative. And then between those x-intercepts, this was positive, so you know between the x-intercepts has to be increasing. You can see that those color codings have to be the same. Okay, let's take a look at B. All right, so if you take a look at B, I'm going to again color code this the best I can. I have something that's increasing, so I have to have 2 areas that are positive and 1 area that is negative. Okay, so it's going to be increasing. I'm going to put just an I for increasing, an I for increasing, and then between them, it's got to be decreasing. Now, because those are like sharp turns, those are going to end up being discontinuities on the derivative. Now, I want you to see this graph has an increasing, they're both positive, and then a decreasing, because this is negative. All right, now those sharp turns, those are going to be breaks. It's only going to be 0. It's only going to hit the x-axis if it's a smooth curve. So the maximum minimums on a smooth curve, that's what gives me 0. So this would match with this. Okay. Now for C, all right, I have something that is increasing in the very beginning. And then I have it decreasing afterward. And it has a little maximum on a smooth curve, so it has to have 1 x-intercept. And I think there's only 1 graph on here that has an x-intercept, only 1 x-intercept, and that's number 1. And again, we can show here that this is positive. Why is that positive? Because the original graph was increasing. And why does it go to negative values? Well, because the original graph was decreasing. So these have to be negative. Now that leaves me with only 1 left, but let's try to support our answer here. Let's try to defend it. Okay, first, if you take a look, I have a smooth curve and I have 3 extrema, which means I need 3 x-intercepts, so that's good, okay? So now I know that it has 2 intervals of decrease and it has 2 intervals of increase. So if you look here, it's going to go positive, and later on it will go positive. And then you can see here it has, it goes decrease, and then it decreases. Okay, so again, those last 2 match up. So trying to match those graphs together. Now, The very end of this notes shows you how to do the derivative or to evaluate a derivative or approximate a derivative using your calculator. So feel free to try these steps. So you can do it in the home screen. Feel free to pause your video, see if you get the same answer as me. You can also do it from the derivative from the graphing screen. So you can graph the function. Second, calculate dy dx, type in the number you want the slope for. And you can even graph the derivative of a function if they give it to you using this notation, okay? Feel free to ask me if you have any questions about that. I can help you guys work through the calculator pretty easily, all right? Have a good day.